Hello and welcome back to Calculus 3. We are starting chapter 14, the first and very quick lecture on vector fields. So chapter 14 deals with vector calculus, and we're going to see a lot of really cool things in this chapter, starting with vector fields. If you are familiar with wind and flow of liquid and stuff like that, then you have magnetic fields and electric field, gravitational field, and so on. Vector fields are what would describe those phenomena. So when you put the fan on, you feel the air that hits your face, right? So the molecules or air are pushed, right, by the blades, and they propel forward, right, and hit your face. So there is a force, right, which is at work there, and we can represent that with a vector. Now, the difference between vector and vector field is vector is one vector, singular, right? This is infinitely many vectors occupying a space. So vector function, right, the vector field is a function which assigns a vector to each point of its space. It could be 2D, it could be 3D. So if you think about the air in the room, and you think about each individual molecule of air in this room, it doesn't stand still, but let's say it sits in its position. It doesn't, but let's say it does sit in its position. As soon as there is a source that pushes it, like a fan, right, its original position becomes the origin from which the vector, velocity vector, force vector, whatever vector you want to think. So that position where the particle was originally becomes the original position, and then you have a vector from that point on. So when I have a vector field function given to me, right, it's a function that calculates each individual vector on each individual particle, and that will depend obviously on the vector field. Vector field is something that you can measure. So they have probes that they throw into a hurricane and a tornado, and those probes read the data and feeds the computer, and it makes the models like that. You have the temperature distribution, you have the magnetic field, you have all of these things. You can measure the field. Now the fun part is, and this is 14.3, when you measure your field, and if that field is conservative, we'll get there, you can come up with a function. You can work backwards and come up with a function which generates that field. Now, when you have a function, you understand the concept. So much of our science that involves fields of any kind, which is gravitational, electrical, right, all of these fields that we're dealing with, if you're able to measure the field, and you have a conservative field, you can come up with the equation that creates that field. When you have the equation which creates the field, you can make the device where that equation plays a role to create fields, right? So we are able to generate electric field, magnetic field, which is the base of all of our technology that we have today. Electrical generator, transformers, and electrical motors to do the work. You transform electrical current into magnetic field, and then a rotor spins inside the motor producing work. So now you have all of this stuff. The only ancient technology that we are still embracing right now are actually our cars, right? It does have alternator there to run all of the electric stuff, but the main propulsion there is you pump in then plants and animals and you explode them, right, which pushes the piston, which turns your axle and it gets the car moving, which is actually now being, we are moving slowly towards the electrical car, which is obviously the next step in our evolution. So we need to get rid of these chemistry-based fuels, like also for, you know, space exploration, right? You pump in the fuel that is exploded, right? It's not oil, obviously, but we can do better than that. So let's put down the definition. It's right there in the box. We'll put down definition for vector field in 2D, and then from 3D you just add one more. So it's vector fields in, let's put the title, vector fields in 2D. So let F and G be defined on region R of R squared. A vector field is a function, use the capital F with the arrow on top, vector, don't forget those arrows, assigns to each point in R a vector f of xy, g of xy, so this thing is written as f is equal to vector fxy, gxy. You can also use ij notation if you want to. So you have your fxy I with a hat plus gxy j with a hat. So that's the definition. Technically, you are focusing on the formula for it, and it's as simple as this. You have xy plane, you have a vector field defined as, let's say, x minus 1 and 3. Let's say this is a vector field definition. How do you generate xy image for that? Well, you have to pick a location at which you want to look for the vector. So let's say you pick a location at the origin. If you pick location at the origin, so f at 0, 0 is going to be 0, minus 1, comma 3. So it's a vector negative 1, 3. So from your original point, you will go negative 1 in x direction and 3 units in y direction. So that's the vector that you have from the origin. If you pick a point, let's say 1, 1, you can pick any point you want. If you pick point 1, 1, you will have 1 minus 1, comma 3. That is going to give you the vector 0, 3. And you are going to have just this, oops, sorry. For 1, 1, it's right there. You are having 0, 3 as a vector. If you pick point 4, 0, 4, 0 is right here. That's where the 4, 0 is. You will plug in x for x. So that's 4 minus 1, comma 3. It's going to be vector 3, 3. You will go 3 units up, 3 units over. This is your vector. So you see that at every point, it's a different vector, right? So which vector you get depends on the vector field function and depends on the starting point. So you can see this vector field somewhat like fans out, right? It seems like it's going to fan out as you calculate more of these. Let's calculate 3,1. See what happens at 3,1, and then we're done with this. Okay. So that's 3 minus 1 comma 3 vector. So 3 minus 1 is 2, 3. So at 3,1, this is 3,1, we go 2 units to the right, 3 units up. So it seems that this just kind of fans out, up, goes up. Let's take a look at another example of this. Some of the very important examples. F equals negative yx field. Negative yx field is a very important field, and then there is also x comma y is very important field. So those are two basic fields that we actually use. So let's discover what this field is. So we calculate values, and then we are going to draw on our xy. So I'm going to use, this is number 1. So negative 1, 1, 1, negative 1 on x and a y. So let's start with f at 0, 0. So that's going to be just vector 0, 0, so we don't get anything at the origin. It's a 0 vector. It's just a dot. Let's do the 4 points that we have on the sides. So f1, 0. Well, guys, this is a little bit tricky, guys. This is your x input, this is your y input, so you have to plug them in where they belong. Your y is 0, so first coordinate is 0, your x is 1. Do you see that? So the vector actually flips the x for y and y for x, right location, and so on. So I have a 0, 1. Right, 0, 0, 1. 0, 1 is straight up. So I have a vector that goes straight up from 1, 0. All right, next one in a row is 0, 1 point. So now my x is 0. That goes on the second one, and this is negative 1 over here. So that one looks like this. And then we have next one, f of negative 1, 0. F of negative 1, 0. So x is negative 1, that goes here, and y 0, 0, negative 1. That is going to be this. And the last one is 0, negative 1. So negative 1 is on y, so that becomes 1, 0, which is this one. Do you see that it spins? Every single one. If you are to compute the halves, I'll do that red. If you compute halves, they will look like this. If you compute twos would go like that. Now, if you go off these axes calculations and you go to any point in between, let's go the blue one, let's say you have f11. f11 will give you negative 1, 1. f11 is right here, Negative 1 on X, positive 1 on Y looks like that. I hope you guys see this from these vectors. This is a fundamental vector field called rotational vector field. Rotational vector fields are extremely important. You do not get to have technology we have today without rotational vector field, because rotational vector field, which we need to create our electromotors that drive all of our industry today, right? We don't use steam power anymore. Our factories are connected to electrical grid, and the electrical motors are plugged into the outlets, and they run all of our machinery that does all of our production, all of the robots, all of the machines, everything. Rotational magnetic field. So we have F negative YX is called rotational vector field. Now you can find the rotational vector field in hurricane and tornado. Sure, they're there, right? But we like to also think of the rotational vector fields for things that we build to make our lives easier. So it's a very important vector field. Another important vector field for us to know is radial vector field, given by F equals just XY. What radial vector field does is radiates vectors out of the source. So you see that vector field calculated at 0, 0 is vector 0, 0. So at your XY graph, it's a dot in the middle of the graph. Let's again do 4 important points, well, 4 easy points. Not important, it's just easy. 1, 0 is the vector 1, 0. So that one is just gonna go out from that point. Vector at 0, 1 is going to give me vector at 0, 1, which is just going to be this. So now, if you use the axes, at 1 you just get these 4 vectors. It's interesting to see what happens if you go F1, 1. Well, that's going to give you vector 1, 1 because it's XY. So that's this, 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 and this. Do you see how there is a source in the middle and it just goes in all directions? Right? Radial field. What do I get as the example of, let's say, three-dimensional radial field? Sun radiates energy in all directions around itself. The heat that we have on this planet, which is caused by sun, is not the heat that is sent by sun, because you just move from the earth a little bit towards the sun and you're going to freeze to death, right? You don't burn to death. It should be, right? If the heat was transferred from the sun, it should be very hot, and then it should kind of dwindle, all right? And then it will be just right temperature on Earth, right? No, it's not the heat that goes through the vacuum. Heat doesn't go through vacuum. Our fusion reactors that are in the research are heated up to 150 million degrees. Sun is puny 10 million. We build machines on the planet that is 150 times hotter than the sun. Cool? Yeah, cool, right? How do you keep that cold? Right? You call a cooler master company and tell you I need a heat sink for 150 million degrees? No. You suspend that in a vacuum. The plasma that we have in those reactors is suspended in a vacuum, the heat doesn't transfer to vacuum. So you don't get the heat from the sun. So no, you're not going to get burned if you drive close to the sun. You can go as close as you want to the spaceship. Right? Nothing's going to go, nothing's going to happen. Right? However, the radiation, the UV radiation that the sun radiates out, because sun is the biggest fusion reactor we have in our solar system, yeah, that's the one. Now that hits the atmosphere, and that heats us up, right? So radial field would be a source that radiates in all directions. Also gossip, right? There you go. You have one person that starts the gossip, which goes in all directions, radial field. That's what it is. So what is vector field? It's simply a collection of functions. Guys, they can be as complicated as you want them to be. Here is another example. The book gives you the example of a flow. And then shear, but the channel flow is a good one. So flow, vector field given as 1 minus y squared, comma, 0. What you get is exactly what they promise, a flow. Get your x-axis, get your y-axis, then you get long vectors going this way, and then shorter vectors on the inside, and very short vectors to the walls. Now, this makes sense. As the liquid goes through the hose or a pipe, or as blood goes through the vessel, I don't care whether you're a plumber or a doctor, same principle applies mathematically. You have the walls rubbing against the liquid, creating friction. So the motion is slower around the walls, and it's fastest in the middle. So what happens is when you have a blood clot, which closes up this, still the same volume of blood is pumped by the heart to go to the smaller opening. So the blood clot over here reduces the blood clot reduces the volume of the hose, which is the blood vessel, and if there's too much pressure, right, of course it's going to burst somewhere, right? So these are the things that are common sense, studied through simple vector field and the flow. Now, do I have a third-dimensional version of this? Sure, I do. 1 minus x squared, 1 minus y squared, comma, 0 for z flow, right? And then it's a 3D. So this is a two-dimensional representation. If you want a 3D, you just add 1 minus x squared as a coordinate as well, and you have it. So it is very simple to draw these. You just have to remember that you are in charge of picking points, and as soon as you pick x and a y, which are the numbers that you coordinates that you pick, you will place those where they belong as x and y variables in the formula, and you will come up with a vector which is going to be numbers, and then you're going to graph that vector. The radial field, rotational field, flow, shear, there are a lot of different fields, and you can come up with pretty much whatever you want. You can just write whatever and have it. Now, the third-dimensional version of this, we're just going to add, z variable and then a third component to your vector field. So 3D vector field is going to be given by f of x, y, z is, and now you have your f, x, y, z, g, xyz and age xyz. So it's again, it's a function which assigns to each point from your 3D space, right? So if you want to work with the wind, right? Well, this is the one that you have to use because the wind happens inside the room, or right? Wind is your, you know, your hurricane and a tornado and the regular wind, and then you have the fan and air conditioning, and right, when someone sneezes, all of that stuff goes in this formula. Some of the images, it's very obviously tedious to draw these by hand, so I'm just going to show the book. We see the flow, right? I talked about the flow. And then you have the whatever is in the middle, and all the way to the right is the radial field, which has 0 as the origin, like where the sun would be, radiates in all directions in space around it, the radiation. The last part of this is to understand that this formula here is a vector of functions. So if that is a vector of functions, then I can take a scalar function and get a gradient of it, and that creates a vector of partial derivatives, right? So every gradient is actually a vector field. Ooh, right? So if I have a scalar function, say z equals x squared y minus e to the x, right? That's that. What I can do is I can find gradient of z, which is partial derivative of z in respect to x, comma, partial derivative of z in respect to y. You just generated a vector field. What is 14.3? 14.3, I give you the field and you have to come up with this. And that's what science is. You go and you measure the field and you use this mathematical technique in 14.3 to come up with the equation, and once you have the model, you can build stuff. That's how science is done. So in Calculus 3, the procedure is called looking for potential function. Potential function is function z, which generates vector field. In differential equations, you will call the same procedure exact differential equations, because it is actually a method of differential equations that you will study in chapter 1. It will be identical calculation, we'll just have a different name because it's in a different course. But you know that differential equations generate 100% of your equations in physics and engineering. Well, engineering is from physics, so physics, and that's the end of the story. Everything goes from physics from that point on. So we give physicists mathematical concept, physicists figure out everything, and then on top of that you can build up the chemistry and engineering and everything else. So now, if I want to create the vector field, I just calculate the gradient of z. That's partial derivative in respect to x, which is 2xy minus e to the x, comma, partial derivative in respect to y is x squared. This thing over here is the vector field. So now, as I said, in 14.3, I give you this, and I expect you to give me this in return after a page of calculations. So all we need to remember today, vector field is a function which assigns to each point in space, whether it's 2D or 3D, it assigns a vector. And you calculate those vectors by first figuring out where you want to calculate, which vector you want to calculate. So you pick a point in space and you compute the vector at that point. You draw that vector and you move to the next one. Obviously, it's impossible to draw every single one because there are infinitely many of them. occupying any space you pick. And last, you can generate your vector fields by having a scalar function and figuring out the gradient of that function. Please don't turn off the computer.
No.
Okay, just leave it, because I need to print another exam.
That's fine.
Thank you all, and see you Monday, right? Monday is 13.2 and review. Tuesday is exam and 13.3, and then Wednesday 13.4. 14, yeah, 14. Yeah, everything 14, yeah. So see you all on Monday.